Hello, good morning. Today I like to discuss the basic physics of semiconductor materials for the students from MSc and 7th semester, 8th semester BTech student for the carrier concentration expressions and shifting of Fermi levels in different conditions. So let us start first the physics of semiconductor. Whenever we talk about the physics of semiconductor, then one point is very interesting, that what kind of material is in our consideration. So we can have this way the materials as this is SI one way, and it is connected in four valenced material. Its distribution function depends upon the density of state. So if we talk about the density of the state and other parameters, then we have to start from the very basic principle of ensemble. Very basic principle of ensemble. What is ensemble? It is the time average as we imagine a large system of our interest, that is called ensemble. And when we call this one, so we can classify in three categories, that is canonical, Gibbs, and Grand. Canonical, Gibbs, and Grand canonicals. This Gibbs canonical is also called microcanonical. This is also called as microcanonical ensemble. So in microcanonical ensemble, it is very similar to the systems as we have our interest in case of the open system, closed system, and isolated system. So canonical ensemble is as the closed system. Closed system. Canonical ensemble is the closed system. Closed system means the volume or way to represent is E plus del E. Number one. Number two, the thermodynamical function minus Ts, temperature and entropy, is equal to minus kT ln W. W is way of arrangement. In case of the system closed, then it has the partition function, and that partition function is Z, and Z is equal to, this is minus E upon kT with respect to T. This is the Z, canonical system. In this microcanonical part, the system is very much, this is E plus delta E, and it is the constant. It is the constant, and then it is the isolated system. Now the third one is grand canonical system. It is considered as open system. It is considered as open system, and the partition function is Z. Z is equal to summation e raised to the power n mu of kT and this minus E upon kT into delta dt. And the system of chemical potential is minus kT ln Z. This is your chemical potential. So any system can be classified in three categories. First is canonical, then gives a microcanonical, and third is grand canonical. So our interest of this is semiconductor material. Semiconductor material is grand canonical system. Grand canonical system. So statistically, we represent this grand canonical system and its various characteristics in case of the phase space. So we have to have the phase space concept, something like we have 3D space, Euclidean space, and that has something like this is X, this is Y, and here it is Z. So any point P can have X, Y, Z, and any volume confining this one is represented as something that is dV is dx dot dy dot dz. So this is the point and there is a space. But whenever we talk about the phase space, then there are three momentum space and there are three position space, where Q is position and P is momentum. P is momentum. So from the theory of uncertainty, that is Einstein's theory, the phase volume, is d gamma, and this d gamma is expressed as dV into d tau. So what is dV? dV is dx dot dy dot dz from this way. And in each component, there is change in momentum dpx. Here the change of momentum dpy. Here the change in momentum dpz. So this d tau is dpx into dpy into dpz. This is dpz. So the same case, that is, here is dpx dot dpy dot dpz. Now we have something that is, this is a volume, and in this case, that is, by taking the space from the equation energy, that is any particle which is moving with velocity v having mass is of the kinetic energy E. This is the kinetic energy, and this is m square v square upon 2m, and this is nothing but p square over 2m. So this p square is 2me. P square is 2me. So in this case, we have the P is under root 2me, and if we select a space of volume, if we select the space of volume something this, having the value P of this, so this d tau is equal to 4 by 3 pi p cube. 4 by 3 pi p cube. What is p cube? 4 by 3 pi, p is 2me, and this is 3 by 2. This is the under root of this part. So we can express this value 4 by 3 pi 2me 3 by 2. This is your d gamma, which is the volume component in this case. Now, if we have the phase space that is this gamma phi, this phi is phase cell is this gamma by volume V. So this is 4/3 pi p cube into V volume, and here this one is H cube. Why it is H cube? Because from the uncertainty principle, we have this one is as dx into dp, dy dpy, and dz dpz. So we have h dot h dot h, that is H cube. So the phase cell phi is divided by this small volume, that is phase volume, through the point H cube. So the phase cell is this, and this can be expressed as R. This phase cell is 4/3 pi V upon H cube 2me 3/2. Now, number of microstates. Number of microstates, that is this d gamma, this omega is del phi by del E. Del phi by del E. So this value is 4/3 pi V, 4/3 pi is V, 2me. This is 3/2. So we have this one is 1/2 into 3/2 into 2m into dE. 2m into dE. So we have this cancel 3. This has cancelled 2, 4. So this value is, we can have this value as, this value is 2 pi V by H cube 2me 1/2 into 2m dE, this part. And energy density, the energy density, is this GE, and this GE is, this one is 2 pi upon V into V upon H cube. This is 2m 3/2 under root E into dE. This is. Now, if we consider the cell from the solid state configuration, then we have the expression. We have the expression SE is equal to 4 pi upon h cube 2m 3 by 2 under root E into dE. Under root E into dE. Now we have to find this expression. We have to find this expression in the state something like this is E valence, E conduction. This is your conduction band, and here it is valence band. So in conduction and valence band, there is a slight modification in the energy concept, and that modification can be expressed as, this modification is expressed as, in case of conduction, this is under root of, in case of construction, this is the under root of E minus EC, E is minus EC, and in case of valence, there is a modification EV minus E, EV minus E. So this is upper limit of valence, and this is the lower limit of conduction. This is the lower limit of conduction. So we can have another concept, that is Fermi Dirac distribution, that is quantum statistical distribution for half spin particle like electron, and the function is, FD function is, this Fe is 1 upon 1 plus e raised to the power E minus EF upon KT. This is the exponential power of whole. This is the exponential power of whole. So if E is equal to EF, E is equal to EF, means E minus EF is equal to 0. So exponential 0 is equal to 1. So F of E is equal to 1 upon 1 plus 1, that is 1 by 2, that is 0.5. It is 0.5. And we can plot this as, the function is something like this. There is energy E, and here the function of energy F of E. Then this value is E is equal to EF. E is equal to EF. This value is 1 and this value is 0.5. So what we have this kind of function when this is T is equal to 0 Kelvin. This is T is equal to 0 Kelvin. And this function is something like change in this as something T1, or there is another change of the function This is T2, where T2 is greater than T1. This kind of the function. And we can have the function in slightly different way, that is energy level function. Energy level. So in case of energy level, we have this. This is E, F, here it is EV, and this is EC. This is EC. So the function is something like this. For electron, and this will be hole. So this function f of E for electron, and this function is 1 minus f of E, 1 minus f of E for holes and electrons. So this one is energy distribution function, but the density distribution function is something like this. GE, that is density function. Here also GE, that is density function. So the resultant function is something like this. This is your EV valence band. This is conduction band. So there are electrons. There are electrons in conduction band. And here it is holes in valence band. Holes in valence band. The carrier density can have GE into FE for electrons and GE into 1 minus FE for holes, the holes function and then electron function. So we can have the carrier concentration of electron can be expressed as NE, weak energy, from EC to infinity, the value SE into FE into DE. FE into DE. By substituting this value, that is EC from infinity, this is 4 pi h cube 2 m star 3 by 2 E minus EC 1 by 2, and then the function is 1 plus e to the power E minus E EC upon KT into DE. So this one is the function, and this function can be integrated with the help of the method of integration. And this method of integration, that is, we have in this case as, suppose E minus EF upon this KT, this whole thing is greater than 1. So this implies that 1 plus e to the power E minus EF upon KT is greater than this is greater than 1. So if you add this one, so by ending this one, we find this is equal to approximate e raised to the power E minus EF upon KT. EF upon KT. So we can also simplify this. We can also simplify this by assuming as E minus EF is equal to E minus EV plus EV minus EF. And if we divide, this one is KT that is required. So the whole thing is divided by KT, or explicitly this is divided by KT, and this is also divided by KT. And we can take this value as the form of exponential. Then this exponential is substituting this value in previous equation. We have in previous equation we have this is NE is equal to, take the constant terms out, 4 by 3 pi h cube 2 m star 3 by 2, and this is infinity to EC E minus EV This is taken out. This is EC, and here it is. This EF is the sufficient value of E, because we are moving from infinity to that particular level. Infinity to that particular level. So the simplified form that occupy this E as this function is having, this is E minus EC upon KT plus EC minus EV upon KT, and one of the part can be taken as the constant, that is something like E. So this E minus EC, and then this E minus EC upon KT this is KT into this EC minus EF. EC minus EF upon KT, and now on substituting, this is EC minus EF EF upon KT. So this value EC minus EF, as from this expression, that is 4 pi h cube 2 m star 3 by 2 E, this is EF. Why it is? Because there is a negative sign as well. This whole is -1 dE. So this is EF minus EC upon KT. These are the constant, and inside the integration is infinity to EC. This E minus EC 1 by 2 into E. This is EC minus E upon KT into DE. Now in this expression, let E minus EC upon KT is equal to X. So E minus EC is equal to X into, this is KT, or minus DE, or you can say this is only DE with plus, is equal to, this is X dx into KT, dx into KT. So in place of this DE, we can substitute this, we can substitute X into KT. So what we find? We find E minus EC is equal to X KT, this value. So this value is from here. And this exponential value is, this is EC minus E. So E minus EC is, you can have minus X. So this can be as it is EC minus E upon kt is equal to minus x. And this minus x will be power exponential. So simplifying all these, we have Ne is equal to 4 pi h cube, 4 pi h cube, 2 m star 3 by 2 e raised to the power E f minus ec by kt integral from ec to infinity, and this ec minus e minus ec is x kt ka half power half minus x into de is dx kt. So we have this kt, and here it is kt to the power 1 by 2. Combining these two parts in multiplicative way, this is kt to the power 3 by 2, and already we have factor here, it is 3 by 2. So we can rearrange, that is 4 pi upon h cube. This is 2m star kt 3 by 2. This is kt 3 by 2 e raised to the power ef minus ec upon kt, and this is ec to infinity, and here under root x e raised to the power minus x and dx. So this part of integral is standard integral, and we can substitute this value is under root pi by 4. Under root pi by 4. So what will be the value? 4 pi h cube 2m star kt 2m star kt 3 by 2 e raised to the power ef minus ec upon kt into under root pi by 4. Under root pi by 4. So this under root pi by 4 is nothing but under root pi by 2. Under root pi by 2. And here it is 4. So this will cancel. This will cancel. And the expression is 2 pi upon h cube 2m star kt, and here it is pi and here it is under root pi. So again, this is pi and we have bracket 3 by 2. And here it is Eg by 2 kt, because Eg band gap is equal to Ef minus Ec, Ef minus Ec, and this Ec minus Ef, and this Ec minus Ef is minus. This is minus, and half Eb minus Ec is Eg band gap. So this is half of this band gap, half of this band gap. And that's why here it is the exponential power minus Eg by 2 kt. And this is Ne. This is Ne. So once this pi is included inside, so there is no need to have this outside. So the function n of e can be written as nd e raised to the power minus Eg upon 2 kt, where Nd is 2 upon h cube 2m star pi kt 3 by 2. 2 pi kt 3 by 2. So, which is constant, at t constant. At t constant. At t constant. So from this equation, we have two important results. First, Ne is proportional to t to the power 3 by 2 from this factor. That is temperature dependence. And second, Ne is proportional to e raised to the power minus Eg upon 2 kT, which is band gap dependent. Eg. So what is the beauty of this equation? The beauty of this equation is we can enhance the charge carrier concentration, by two methods. First, by temperature. And this is N of E proportional to T to the power 3 by 2, and this is known as intrinsic semiconductor. This is intrinsic semiconductor. The second one is by reducing band gap. That is Ne proportional to e raised to the power minus Eg upon 2 kT. This is extrinsic semiconductor. Means band gap can be reduced by doping of impurities. So these doping of impurities are two types. These impurities are of two types. That is trivalent in A size semiconductor. So this is p-type semiconductor. And second, pentavalent in Si semiconductor, that is n-type semiconductor. Now, one important thing should be kept in mind here. Note, in case of metal, the free electron the free electron can be written as Ne proportional to T square into e raised to the power phi upon kT. E raised to the power phi upon kT. This e raised to the power phi upon kT gives the information regarding the work function. That is square, and here it is the work function. Phi is work function. And that's why oxide coated materials are used in case of filament, especially in case of the materials, something like tungsten, something like molybdenum, and then barium oxide is coating over the filament, especially in case of diode, so that at a low work function, the electron may be increased in from the metal, and this one has very good use in case of the materials. So this one is a basic difference, that is in case of work function and in case of temperature. So the metal has this kind of the expression, which is very similar to the semiconductor materials with certain variation. So what will final way we will see in later, after considering the whole concept for the holes. This is the case of the carrier concentration of electrons. We can have the carrier concentration of the holes also. So for expression for carrier concentration of holes, carrier concentration of holes. So the carrier concentration of holes is very simple, and it is based on the assumptions that the absent of electron, that is called as hole, and we consider here it is p-type semiconductor, that is hole, and the function used is 1 minus f of e. So as we see, this one is a EV, here it is EC. Once electron from valence band leave to the conduction, so here it is f of E. The function of electron is gone with the FD distribution, Fermi Dirac distribution, and this part, this is converted into the whole, and the function is 1 minus f of E. 1 minus f of E. So this one is the whole function, and here it is, this one is electron function, and rest of these things are similar. So this one is a whole, and the carrier concentration, suppose n of p, the whole concentration. So the expression can be written as an n of p, that is from minus infinity to EV. This is the maximum, so we can say this is minus infinity to EV, and this is SE function, and here it is 1 minus f of E, 1 minus f of E dE. What is the function f of E? Now we can have this part as 1 minus f of E is nothing but, we consider this is 1 minus 1 upon 1 plus e raised to the power E minus EF upon KT. So this function is nothing but 1 minus 1 plus e raised to the power E minus EF upon KT, and this is power minus 1. So what we have, this is 1 minus 1, this is 1 minus 1 plus e raised to the power E minus EF upon KT, EF minus KT. So this 1 cancel. We have finally e raised to the power E minus EF of KT. EF, that is 1 minus F of E. So this is the function of whole. This is the function of whole. So in place of this whole function, we can express. So by substituting, we have NP is equal to, this is minus infinity to EV. This is SE into this value is e raised to the power E minus EF upon KT into DE, this function. And this is based on 1 plus x to the power minus 1 is equal to 1 minus x. This is the binomial theorem. This is the binomial theorem. By using this binomial theorem, we can have this expression in this part. So that is there. Now here we can have this function as, we can write the complete function, that is minus infinity to EV, and this SE is 4 pi h cube. This is 2m star of P. This is 3 by 2, and here it is EV minus E into, this is E exponential power E minus EF upon KT into DE. This thing is. So we can have this one E minus EF upon KT is equal to e raised to the power E minus EV plus EV minus EF. This is whole of KT, and this is nothing but e raised to the power E minus EB upon KT into e raised to the power EV minus EF upon KT. This one. So substituting this value, substituting this function and its two breakup, that is E minus EV, EV minus EF in the above expression. So we have this one as N of P is equal to 4 pi upon h cube, 2 MP star 3 by 2, and this is EV to minus, sorry, this is This is minus infinity to EV. This is minus infinity to EV. And this EV minus E 1 by 2, and this is E minus EV minus E upon KT into EV minus EF upon KT into DE. So this term is constant. This term is constant. So taken out outside, that is 4 pi h cube 2 mp star 3 by 2 e raised to the power EV minus EF by KT integral minus infinity to EV. This is EV minus E 1 by 2 e raised to the power minus EV minus E upon KT into DE. Now putting the value EV minus E upon KT is equal to X. Is equal to X. So by substituting this value R, this EV minus E is equal to X into KT. X into X into KT. Once you are differentiating that this is 0 minus DE is equal to dx into KT. Dx into KT. So DE can be retained from this place, that is minus dx KT. So this value is 4 pi h cube 2 mp star 3 by 2 exponential EV minus EF by KT integral minus infinity to plus infinity. This EV is equal to X. This is X KT to the power 1 by 2 e raised to the power minus X. This is minus dx KT. Dx KT. So what we find, this KT and here it is KT. This is 1 and this is power half. So we can take it common, both 4 pi h cube 2 mp star KT 3 by 2. And this is E. Here EV minus EF. EV minus EF upon KT. This minus integral can change the limit. This minus infinity to plus infinity, or you can say this is EV to infinity. EV to infinity. And here it is under X. This is minus X into dx. And then this standard integration is under root pi by 4. Under root pi by 4. And this under root pi by 4 is under root pi by 2. So this 2 cancel and this pi, and here it is pi. So 2h cross h cube 2 mp star. This pi 1 and here it is under root pi. And this is KT 3 by 2 e raised to the power minus EG by 2 KT. From where this EV minus EF is equal to minus EF minus EV. EF minus E, which is equal to minus EG by 2. Minus EG by 2. So this one is the expression N of P that is carrier concentration of the holes. And this can be written as N of V e raised to the power minus Eg by kT. This is 2 kT. So we can have the same explanation as in earlier case. It is there are two waves. The whole concentration, can be increased through two ways. First temperature, that is T as Np proportional to T to the power 3 by 2. And second, band gap, that is Eg, and this is Np proportional to minus Eg by 2 kT. So this Eg must be reduced. So that reduction is in this case is p-type semiconductor. P-type semiconductor is required for this purpose. So we have these two equations, that is for finally we have N of E energy, that is 2 by H cube 2 Mn star, that is effective mass K pi 3 by 2 e raised to the power minus Eg by 2 kT, that is Nd e raised to the power minus Eg by 2 kT is constant, and the second is N of E, which is 2 upon H cube 2 Mp star for holes kT 3 by 2 e raised to the power minus Eg upon 2 kT, that is N of V e raised to the power minus Eg upon 2 kT. So these two expressions for the whole, this is we have expression for electrons and holes. So this is the today first part, and through this doping we can have N-type and P-type material, and there will be shift of Fermi level, which will be discussed later on. Thank you.